So this is lesson 6, and it's about evaluation of our models and how to improve the performance. So hypothetically, we have a model, we've started on our machine learning path. How do we see how well it's actually doing, and how do we improve the performance? So I'm going to start by saying let's see. We're going to skip some of this. These are different other classification metrics. We're going to skip some of this and go to here. Okay, so I'm going to start by saying a little bit that I've been lying to you just a little bit, because the score that we are reporting is not the score we actually want to use in production. And why is that? Well, especially with more complex models like decision tree, remember I said there's a reason why we would want to stop it from going too deep. And that is because if we let it, it will ask every kind of question until it perfectly classifies every data set. But does that generalize well to unseen data? No. Thank you for the engagement. So the problem there is, yes, we can pretty easily get 100% accuracy with a decision tree if we ask every question there is to ask, so that we perfectly just classify every person on the Titanic, for example. But that has what we call high variance, meaning if we put a new group of people on the Titanic, it probably won't do that well at predicting this new group of people because it was so well fit to that last group of people. So for some example, that's called overfitting. So here's an example of some data behind me that has been underfitted, a good fit, and overfitted. So this data has, we can kind of see the trend of the data, and that's where that good fit is. We can see that just fitting a line through the data is underfitting it. And that's what we call having high bias, because it's kind of like someone who's just very set on their ways, and they're like, I'm not gonna budge at all. And so that straight line has high bias. But then on the other side, we have an overfitted line. And see how that line goes through pretty much every data point. And so if we're trying to model this data, if we throw a new set of data at it, the model will be completely different. And so that model varies a lot from data set to data set. And so that's what we call a high variance data set. And so this is another jargon alert or terminology that I've given you a few of throughout the course, is what's called a bias versus variance trade-off. And it's also the trade-off of underfitting versus overfitting. So an underfitted model is one that has high bias, an overfitted model is one that has high variance. And so when we are making a model, we don't really care. What we've been doing so far is we've been reporting the score on the training data, on the data that we gave it. But what we really care about is how well does it do on data it's never seen before. Because traditionally, right, if we have a machine learning model that we're using to predict anything, like we were talking about predicting the network connection, given a number of hops, we want to see how well will it do on deploying it to the field, where we want to ask it, okay, this is the number of hops we are given, and we want it to tell us the network connection. So that's unseen data. So what we're going to care about is, what we need to do is split our data. So we're given maybe 100 people on the Titanic. How we can kind of make it so there's unseen data, we call that test data. And so we're going to maybe give it, if there's 100 people in our Titanic data set, what we'll actually do is just give the machine learning algorithm maybe 80 of the people. And we'll withhold the last 20 people. And so we'll fit the model on the 80 people, but we'll score the model on the 20 unforeseen people. And we'll see how well it does on that. So that's called a train test split. It's actually really similar for in college, or any class. If your professor is looking at the overall problems they could give you in their class, the professor might think, okay, I have this list of 100 problems that I could give them to teach them this material. But I don't want to give them all 100 problems in class. I'll give them 80 problems in class, and then I'll reserve 20 of the problems for the test. Because if they really learn the material, their learning will generalize well to these unforeseen problems, right? So I know I've done some math classes where you can practice, and as you practice, if you don't practice at all, you're kind of like this linear line. You don't know the data at all, right? But as you start practicing, you start kind of learning how to do the problems. What happens if you keep doing the same problems over and over again? Eventually, it becomes almost muscle memory to solve the problems. And at that point, you're not training well to the general knowledge of the problems. You're just training yourself to solve those specific problems. And that's when you know you've overfitted. So our goal is going to be splitting the data into testing and training data, and then training it on the training data, and then testing it or scoring it on the test data. Let's see. So that's what we've done. All right, so here's this plot from before, and it's kind of a question, can you tell which models have underfit or overfit the data? So remember, this is what underfitting or overfitting looks like, but this is from a two-dimensional, from the top looking down. Can you see? So the 3 rows are 3 different. So here's like our data. It's a little hard to see the blue and red, but just take any one of these rows. So maybe take this row, and this is called moon data. So the red lines are like here, and the blue lines are here, or the blue dots are here, if you can't see that well. And then these are all these different kinds of classification algorithms and their decision boundaries. And can you tell which ones have maybe overfit the data and underfit it and done a good job of it from the pictures? Oh, it's really hard to see the titles.
Linear SVM is underfitting.
Yeah, so like Tobias said, this is a linear SVM, and it's underfit because it's like it's underfit. It's the 2D version of that line that we saw above. What about one that's overfitting? Yeah, I know you can't really read it that well.
The decision.
Yeah, the decision trees overfit, so the decision tree, even I can't read it that well. But if you're on your computer and you see it, it's there. So this is the decision tree, and it's created all these little boxes to where it can pretty much perfectly classify every little point. But at that point, it's pretty much just learned these specific points. It hasn't generalized well to like the pattern of the data. And generally, there's 2 ways. Oh yeah, so why does overfitting happen? Well, there's 2 ways models can overfit. One, because our model is complex by design. So like a decision tree is a very complex model versus linear regression is not complex. So decision tree is going to be more likely to overfit. And the other one is if we train our model for too long, or like allow it to grow too big. And so again, for the decision tree, we kind of if we allow it to grow too big, then it can classify every data point. And we actually don't want it to do that. So back to the random forest is better, or do I say that later? Yeah, so back to random forest is better is because we give each random forest, it's kind of like we're doing a test train split for each tree in the random forest. We only give it a subset of the data. And so each tree sees a subset of the data, and then all together they collectively make a prediction based on their little bit of the data. So not any one tree can overfit to the whole data set. So here's an example. Okay, so we import the Titanic data, and then we predict. Okay, so this is how you do a test train split. It's just a command here that you import from sklearn. Do sklearn.model selection import test train split. And you give it the features and your target. By the way, sometimes I write random state, and you probably won't need to do that. I do it for lecturing reasons because when it does a test train split, it does it randomly. It chooses randomly what data it's going to put in the test and the train. But when I teach, it's nice to have the same results every time. And so by seeding it, by doing this, I'll get the same results every time. So if you don't put this, you'll get different results every time. Because there's randomness. So just a note on that. Well, now, a note on when you do a test train split, it's important that the same kind of data is represented both in your training data and in your testing data. So think back to the cancer. If there's only 100 people in the overall data set, we would want to make sure that, and we did say a 50-50 split of testing and training, we'd want to make sure that 50 of those people with cancer were in the testing and 50% of those were in the training. So that's called, you can ensure that by doing stratify. And so see here, if I didn't have this stratify in there, then we the overall percent of people who survive is 0.38. But without the stratified, there's only 0.35 people that survive in the test data, and 0.4% of the people survive in the oh, this should say train. But see how it's different? We want those to be the same. So if you pass stratify equals target, then you should have about the same in both the test and train. All right, that's just a note there. So now we've done a random forest classifier, and we did .fit on the train and the X train and the Y train. And notice the difference. So, oh no, up here. So a decision tree we say can overfit, right? And that's what we can see, right? What we can see here is if we do a .fit, if we call .score on the training data, it's almost gotten 100% classification. So it's doing pretty well, right? But if we try to see how well it generalizes to the overall data, the testing data, it's much lower score. And that's why we always want to predict the testing score, not the training score. Because the testing score is really how well it generalizes. Otherwise, it'll just overfit our data. Now remember, we talked about how random forest doesn't overfit as much, and that's what you can see here. The training score is lower, but that doesn't really matter. What matters is that the testing score is higher than it was up here. Because a random forest it can generalize better. It doesn't overfit your data as much. So what you're seeing there, so see how in this case, your training score is really high, but your testing score is low, whereas here they're about the same. So this is a plot of that. Complexity is, like, our decision tree is allowed to be very complex because it's allowed to be very deep. And so as so over here we have pretty much a decision tree. And what was happening is our error on the training data was getting really low, but at the cost of the error on the testing data getting higher. So as your trees as your model gets more complex, like as your tree is allowed to grow deeper and deeper, your training data error is going to go down and down, right? Because it's getting better and better at classifying training data. But the cost of that is it's getting worse and worse at generalizing. And so that's why you saw the decision tree had a really high training score but a low testing score, so the decision tree would be over here, right? But the random forest had about the same training and testing score, so maybe that was over here. So we want to choose the model which, before our error on the testing data starts going up. All right, so that's all good. But one problem with that is we talked about how it's possible, since we're just kind of randomly splitting the training and testing, that in our split, there's the data isn't really represented the same in our testing data and our training data. And so what we want to do is split it several times in different ways. And so like maybe if in the Titanic data, maybe we first want to take the first 20 passengers as the testing data and calculate a score on that. And then we want to take the next 20 passengers as our testing data and calculate the score on that. And then we want to take the next 20 passengers and calculate the score on that. And so we do like a lot of test train splits over our entire data set. And that's called cross-validation, or another name is k-fold cross-validation. And so it's just like the test trains that we just did, but it does that multiple times in different combinations over your data set. So it's really easy to do cross-validation. You just call cross-validation score. And you can see here that we've passed CV, meaning cross-validation equals 5. So that means it's going to do 5 test train splits. And you can see here that when we print scores, we can see 5 scores that every time. So every time it split the data, it got a score on the testing data, and that's what we're seeing here. So we can do like .mean to get the mean score. All right, so the takeaway from that is when you fit your decision tree or random forest or any classifier, that's what you're going to want to do is do a test train split and then report the accuracy on the testing data. And that's going to be the accuracy that you want to like report to your stakeholders or your boss or whatever. Next is cross-validation. Oh yeah, we did cross-validation. Okay, so remember how I said, so one thing you see here, so number of estimators, this is random forest, right? So I said we could pass nothing. sklearn allows us to pass nothing in there, but if we wanted to improve performance, we can start passing parameters into our random forest and start controlling like doing fine-tuned controls, right? But so here I've passed number of estimators equals 100, meaning the number of trees equals 100, and here I've passed max depth equals 5, and we saw what max depth does, right? And we got a train score of 0.72. But what if I do max depth equals 50? Then our score goes down, okay? What if I do number of estimators equals 10? Our score goes up a little bit. So then what if like number of estimators equals 10 and max depth equals 10? Okay, it's okay. What if I do number of estimators equals 1,000? Take a little bit. Number of estimators is number of trees. Let's take it one. Okay, 0.70. So the idea is a lot of machine learning is very experimental. That's actually one of the things I don't like about machine learning is it's a lot more less mathy than you would think. It's a lot more just like let's throw all the like methods we know at it and try every little like last tuning parameter. So the fancy name for these things are called hyperparameters. They're like what should we put the max depth at? What should we put the number of estimators at? And I wish I could give you like a mathematical answer that like mathematically like this is the right answer. But unfortunately, a lot of machine learning isn't like that. It's very experimental. And so it's really just, well, try everything and see what works best. And so you don't want to manually for like days be like, well, what if it's 10 estimators? What if it's 20 estimators? You want the computer to be able to do that, right? You would think the computer should do that. So the computer can do that, and it's in something called grid search. So in grid search, you pretty much put all the different kinds of combinations of hyperparameters you want to try. So maybe we want to try like 10 trees, 50 trees, 100 trees, 1,000 trees. And then maybe we want to try max depth of 5, 10, 20, 40, or 80. And then there's there's other like hyperparameters, right? So we just throw all these hyperparameters and then what grid search will do is just try every combination. And it will do that for us like all in one pipeline. And so we just hit run, and then we might have to wait a little while, but it will pop out what the best combination of hyperparameters are. And so you can see here, this is like, it's showing, okay, these are all the different combinations that I'll try. And then this it just takes 2 minutes. I mean, with grid search with like bigger models can take like hours or days, but yeah, it prints out. So then when you're done with grid search, you just do best params, and it will tell you the best max depth is 5, the best number of trees is 50. So, and then there's some other things here that's telling you. But the idea is it pretty much will tell you like what the best parameters are for your data set. So it's kind of like a no-brain way to just throw your data set at it and then let it try everything, and then it returns you an answer. So it's kind of like an automated way to do it. So then, okay, you have these, and then you can get the best score. So this is like pretty much 0.73. So that's like, okay, I tried every combination of what you gave me, and the best score I could get on the testing data was 0.73, which is a little bit better than what we got up here when we were just trying different things, right? We got 0.6. All right. So yeah, I mean, really, that pretty much gets you to the point at which, like, a lot of Kaggle competitions do everything you've been learning over the last 3 days. It's all about just importing the data, doing some visualizations on it, crunching it, and then a lot of people use random forest, or there's a few like advancements on random forest, but really they're just some clever tricks. If you know random forest, you can call the other library. Like for example, there's this one called AdaBoost that I won't get much into, but call it the same way you would random forest and just think of it as a random forest, and it is a random forest. It just has some extra little tricks to it. So that's like what the top people are using, and now you know about overfitting and how to choose the best hyperparameters for your model. Machine learning is very experimental, so that's kind of the best I can give you. I think what's best is for you to learn by trying. So if you're feeling like overwhelmed by the lectures, that's okay, it's completely normal. It's kind of not desired, but like I wouldn't want to bore you. I would want to give you like a little bit more, and then as you work on a project and I can help coach you, then I think things will really start to click and you'll be like, oh, okay, I see like why I'd use that or that. And that's the idea. Because I could stand up here all day and tell you 50 different models, but I don't think it would be very helpful to you. So it's nice for you to experiment on your own. If you want on your own time to watch this video, it explains an ADA boost and how that's a slight improvement on decision tree, but you'll see they're actually very similar. In the project work, you'll fit a random forest to your data set. So you should have just fit a decision tree. If you haven't, finish that, and then fit a random forest. And in the last lesson, make sure you print your model and your feature importance. Anyways, fit a random forest, use test train split, print your learning score and testing score, and then use cross-validation and report the mean score, and then use grid search to pick the optimal hyperparameters for your model. And that's about it. Of course, I'm going to stick around to help you with your projects. I'll be here tomorrow as well, which will be like just project day. It'll just kind of be like a data science hackathon. And if you're working on like Titanic or housing, if you have actually that was good enough for you to start with, but now that you've been through the course, you might have some ideas of your own data that you want to process. So you can switch projects even to work on some of your own data that you have like in your job or something. If that's more interesting to you, we can look at that tomorrow.